So we start off with the big idea that we've been dealing with the whole time. The derivative is the slope of the tangent line. Sometimes you forget that because we're at 20 shortcuts already, right? So sometimes you get too bogged down in shortcuts and doing stuff that you forget. Every time you're doing that, all you're finding is the slope of a tangent line. And if you have the slope of a tangent line and you have a point, you could find the equation of a tangent line. So this first question is something that we've done already. We've got a function. We're going to have to use our shortcuts for it. Can we find the equation of the tangent line? Well, what are the two things that you need to find an equation of a tangent line? A slope and a point. So we can get the point by plugging in 0. That's no problem. Get 0, 0. The slope you're going to need to get from your derivative. And we have a product rule here. Keep the first one the same. Derivative of the second one, then keep the second one the same. Derivative of the first one. And then we have a plus 2x at the end. You have to do the derivative of that as well. So we get a plus 2. And you want to find the slope at x equals 0, so we plug in 0 for x. You're going to have to know your pi plate a little bit. What is cos of 0? 1. So then that becomes 1 plus 2, which is 3. And now that you have a point and a slope, you could find your equation of your tangent line. No problem. Now, what is a slope? Slope is a change in y, your rise, over change in x, your run. And so you are finding an instantaneous rate of change at that moment. The tangent line would always have that same rate of change because it's a straight line. So our first idea here is that we think of derivatives as a rate of change. Right? We know that it's actual instantaneous rate of change. If we want to know if something is increasing or decreasing, we can just look at the sign of the derivative. A positive derivative means that you have a positive rate of change. Your y value is increasing as your x value is increasing, which would mean that your graph is increasing. So if the derivative is positive, your graph is increasing. If your derivative is negative, then your graph is decreasing. So how do we just conceptually think about this in terms of questions? Well, in real life, we often make equations that model something. And now if you have an equation, we've learned, oh, we can take the derivative of everything. We're like, we learned every shortcut. Well, what does it actually mean if you do that, right? You're like, someone's studying frogs in a swamp. Sounds like a very fun thing to do. Maybe not in November. But maybe summertime, I could enjoy watching frogs and studying them. And I come up with an equation that represents their population. I make that function f of x. And I'm like, oh, I just learned calculus. I could take the derivative of this equation. What would it mean? Well, a derivative is a slope. A slope is a rate of change. So you would be finding the rate of change of population of frogs per year at whatever year you found. So you could be like, wow, at this year it was really increasing a lot. What happened that year? Oh, that was the mosquito year as well. So they must have had lots of food. Something like that. You could make those kind of inferences from those equations. So you make a new equation. F of x is the rate at which a population of AP students increases in a school, and then the units are nerds per year. What would what would f prime represent? Well, f of x was already a rate. And the derivative is a rate of change of a rate. So it would be here the rate of change of the increase. So your units would be nerds per year as a result, because you're doing a rate of a rate already. So every time you do a new rate, you would add a new per something, whatever your unit of. If you were using hours, if your first thing was something per hour, your next derivative would be per hour, which would be like per hours squared. If you think of it, what's the derivative of displacement? Velocity, right? And that's meters per second, kilometers per hour. What's the derivative of velocity? Acceleration. How do we measure acceleration? Meters per second, or meters per second squared. So you've already seen this rate of change of a rate of change if you've done velocity and acceleration. But it just kind of sometimes seems weird when we say per year. It's perfectly fine to write things that way. You will get some questions where you're going to have to write the units per minute. Or you could write per minute squared. Number of bacteria in a colony after T hours is given by this equation. So now we're getting an insight into how people who know calculus, who are studying things that have equations, can use those equations to figure something out. In this case, if this is population per hour would be a growth rate. So what's happening after 10 hours? Are these bacteria increasing, decreasing? What number would I get? Well, I could find my derivative. It's a really easy derivative in this case, 6t plus 15. And if I plugged in 10, the instantaneous rate of change at 10 hours is that you would expect 75 more bacteria in the next hour. Now, just to help you visualize and think about this contextually, you realize this is a problem, right? I don't know exactly what it looks like. It might be all the way up, it might be different, okay? What we did is we said at 10, comma something, this slope is 75. Now, I'm going to actually plug in 10 into that equation. I'm going to get 300, 450, 1250. Would you agree? Does that look like I did the right math? 10 squared, 100, 300 plus 154. Yeah, 1250. Now, what happens when you plug in 11? According to my instantaneous rate of change, at 10 hours, it's changing at approximately 75 bacteria per hour. Now, you know how parabolas work. Parabolas increase faster than lines. So, if I went on this line, my tangent line, on that tangent line, I'm going to have 11, and if I add 75, I'm going to get 1325. That's going to be on my tangent line. On my actual equation, if I plug in 11, so 3 times 11 squared plus 15 times 11 plus 800, I get 1328. Okay? Well, the parabola is increasing a little bit faster. We know that already. But our derivative gives us a pretty good estimate in saying that if it's increasing at 75 bacteria per hour, and I figured that out in this moment, I can use that to estimate what it's going to be in another hour. But because the tangent line is a little bit off, I know that my estimate's not going to be perfect. In fact, if I kept using my tangent line for 5 hours down the line, it's not very accurate because my rate of change is always changing at different points. But my tangent line can provide a good estimate. And it's something that we're going to use as an approximation. And in fact, people will be like, oh, it's changing at about 75 bacteria per hour, so I could expect 75 more in the next hour as an estimate. That could be very helpful. Even though you know that it's not exact, your calculus gives you a pretty good estimate. And we were only off by 3. That's pretty close. And that was a whole hour. Anything that you would estimate closer to that line would be even more accurate. All right. Part B, show that the number of organisms will always increase. So what I do is I find out with my derivative where it's equal to 0. And that happens to be at negative 5.5 over 2 seconds, which is in the past. If I look at a number line and I plug in negative 5 over 2, and I check my derivative, and I don't know if you remember doing number line things in inequalities in grade 11, but this is similar to that. When I plug in anything bigger than negative 5 over 2, I get a positive number. Anything less than negative 5 over 2, if I plugged in something like negative 7 into my derivative, I would get a negative number. We're going to find out graphically that whenever your derivative is positive, your graph is increasing. Whenever your derivative is negative, your graph is decreasing. I mean, this is a parabola. Do you see that this is pretty obvious? Apparently, negative 5 over 2 happens to be the x-coordinate where it switches from decreasing to increasing. Why will this be always increasing? Well, time has to be bigger than 0. And everything bigger than 0, your derivative is positive. Why is this not realistic? Well, eventually you run out of food or something chaotic happens to a population. In fact, they have a branch of mathematics to study this event. Does anybody know what it's called? It's called chaos theory. What happens when things go chaotic? Right? You were studying your frogs. Populations were increasing. All the frogs were happy. And then they ran out of food. This causes a problem. And the population goes into a crazy kind of moment, chaotic moment, until it equalizes again. And then we have happy frogs for a while until the next chaotic event that happens. So we could think about that for human population. Is it possible that we could run out of food? Absolutely. What would happen? Something chaotic. And it would be chaotic for a while, and then it would relax again and we'd be back to normal. Well, but we went through a chaotic experience. I don't think those chaotic experiences are very much fun, right? Like, what's going to happen if the temperature of the Earth keeps on rising? We're going to experience something chaotic. Is it going to be very much fun? Probably not. But then we'll figure things out and get it back to normal, right? And probably wished we would have figured things out earlier. That's how life generally works. But we'll probably go through something chaotic, unfortunately, first. So we'll see. I'm hoping that that chaos happens, like, not for a while. Oh yeah, here's the mosquitoes, but this is in a controlled laboratory experiment. You just go into a room of mosquitoes. This sounds like not as fun as the frog one. And the population is modeled by this equation. Now, the interesting thing about population equations is often they involve the number e. Because when things grow continuously, I don't know if you remember the PERT formula from grade 12 pre-calculus. Continuous growth. Populations often involve continuous growth. And so we have this equation. Now on this one I'm going to use my calculator a little bit. Now finding the derivative definitely can do your chain rule here. Right? I probably have an arrow saying chain rule. Yeah, there it is. Right, because we have the 0.09t is inside of e, so e is your outside function. And the derivative of e is itself, keep the inside the same, and then multiply by the derivative of the inside. Now if you want to find the growth rate after 5 days, we could take this derivative and plug in 5 and get this answer. But I want to show you, because this would be a calculator part of your test, I want to show you a couple things you could do as well. So I'll let you write that down. Here, I'll let you write everything down. This doesn't seem so bad. 35 mosquitoes a day, I could handle that. If it was like 15,000 mosquitoes a day, I'd be a little bit more nervous. But it is exponential growth. We'll use our calculator to see if something crazy could happen if you kept this experiment going. So first of all, a review of some really nice things that you have on your calculator. So open my calculator up. And first thing I'm going to do is, I have an equation, I can throw that into y1. So I'm going to go to my y1 and I'm going to type 250 e to the exponent 0.09. I don't have a t, so I use x. And I mean, I could graph this. It's exponential, makes sense that it's increasing like this. Okay? Now, it asked for the growth rate. The growth rate is a rate of change, which is a derivative. So anytime something's asking for a rate, it's asking for a derivative. And instead of actually figuring out your derivative, you have that under math. I have it as number 8, the n derivative. And it says, what would you like to take the derivative of? I would like to take d dx of, and I could either type in the equation that I have, but since I have it in y1, I'm going to go alpha f4. So your alpha lets you do a whole bunch of extra menus from f1 to f4. And f4 is your y variable, so I can just put y1 instead of having to retype it. And we wanted to find the growth rate at x equals 5. So we got 35.287. You could just say the answer to 3 decimal places, I got it from my calculator. Perfect. Okay? What's really nice about this is I can highlight this again, and I can say, well, let's say you did this for like a month, 30 days. 334 mosquitoes per day at the 30 days. You spend a year doing this. Highlight it again. Oh! Oh no! 15 zeros. I've got a little chart here that I have from grade 6. That would be 4 quadrillion mosquitoes per day. It's going nuts in there. Yes.
Can you show me how you got to that again, please? Because I missed it.
Okay, no problem. So, first of all, in y equals, we typed in our equation. This is really good to ask because sometimes you just miss one button and then you're lost, right? Then to find the derivative of the calculator, hit the math button. And number 8 has n derivative. I'm wondering if it's in any of the shortcuts too. Yeah, it's in alpha F2 as well as a shortcut. And derivative is 3rd. It's like people like to use it more often. So once you have that, whoops, here we go. So I go math and derivative number 8. Then I can go ddx. I can get y1 from a shortcut menu. I can also get y1 under variables. So if you hit the variables button, and then you want y variables, and then you type functions, they're all listed there as well. Important to know where buttons are though, because you don't want to be on your exam going, all right, just looking for things on my calculator. And then you can figure it out for any x value you wanted. We wanted x equals 5. So at 5 days, there's only 35 mosquitoes per day. If you kept doing this for a year later, you could be expecting 4 quadrillion mosquitoes more in there per day. And you'd be like, lunchtime. All right. This is when it's nice to be November. So some of these rate questions are going to be... My video is paused. We could do the same thing on our calculator. This time I'm going to go to my calculator and I'm not even going to type it into y1. I'm going to use my shortcut this way, get the n derivative, do d dx. My original equation, 34 plus 90. I could write that right in here. When x is 10. And I get the negative 2.44 the same way. So you could type the equation into your graph. Often we like to put it into our graph because then we can figure out other stuff. Like it might ask a maximum, it might ask a minimum, it might ask a value at a certain point. So it's helpful to type it in to y1, and then it's easy to plug in y1 into here. But you could just directly type it into here as well. Okay? So as a calculator question, you could just say, I put this into my graphing calculator, I got the answer. If your answer is right, they'd be like, yeah, you probably did put it into your graphing calculator and get it right. If your answer is wrong, you're like, yeah, you probably don't know what you're doing. We can deduct marks. Yes?
Could you do this also directly on the graph?
So if I would... I can't copy and paste, but like, so if I clear this out, okay, and I'm going to write 34 plus 90 e to the power of negative 0.2x, and I graph it, there's my decreasing exponential function. Then if you go second calculate on your graph, it has a dy dx as well. So we can go to number 6, and say when x is 10, does it let me type in 10? It shows me the negative 2.4 that way as well. Is that what you're talking about? Yeah. So that's kind of nice there as well. So if you have it in the graph, yes, second calculate shows you all the different things you can do. And we have the derivative there as well. Okay, we are going to do one more. I'm going to leave the last one for the next time. Then I've got some problems to challenge you with that we're going to work on. So the percentage A of the market that is Blu-ray players. Does anybody know what a Blu-ray player is? What were they? They're like DVD players, except they were supposedly better than DVD players. How many of you, when was the last time you watched a DVD or a Blu-ray? Probably been a while. Can you still buy them? Yes? Is it like collectible now? I don't know. All right. Here we've got a model. It's since 2006, so maybe this was more relevant then. I'm guessing that none of you put on your Christmas list, I really like a Blu-ray player. Yeah, there was, you know what was before? Okay, so Blu-ray, before that DVD. VHS, but there was something in between VHS and DVD that never happened. It's like, I think it was called like Beta. They were like slightly smaller than VHS, but never, and supposedly better quality, but then DVDs came along and said, this is way better. So, oh, the good old days when you had to go rent a movie. You couldn't just stream it, pirate it off the internet. Find A prime. So this time you would actually have to find it, because it's not a calculator question that says find it at a certain point until part B. So we do our chain rule. We can simplify if we want. And the negative 90 times the negative 0.12 is 10.8. And what does this mean? This is the rate of change of the percentage of the market that is Blu-ray players at time t in years. So it's very important that you state that it's a rate of change. And then you state what it is, percentage of Blu-rays at time t. Because your rate of change would be percentage per year. So then when we evaluate A prime at 5 and get 5.9, this would be 5.9% per year. And it means in 2011, the percentage of Blu-ray players was increasing by 5.9% per year. And then Netflix came along and destroyed everything. What do you think the next thing is going to be? A subscription to like a video platform where you just go and say, AI, I'm in the mood for a romantic comedy involving, and you say where you want it, and then it just makes you a personalized movie according to what you want. Right? And I would like it to star Scarlett Johansson and Caleb. And then you get your unique, don't you think that would be terribly entertaining? People would be sharing videos like, look at the movie I watched. But you would subscribe to this AI video platform that's better than Netflix. And then you could, maybe your movie is the best movie of the year that you came up with the idea and just got AI to do, and you win an Oscar.
Or like you make a new one.
Yeah, I don't know. Is that the next thing?